let me see if I can get OneNote up and going too. And all right, so I see something of it. I can share this, I think. Good. Now let's see if I can actually find where we left off. That would be nice, possible. Maybe this is some of it. Perhaps. Let me see. No, this is the wrong class. So that's it. Let me see what happened before, though. This is something we did, but I don't think it's where we left off. Here, I was just doing a problem by hand. So I think that may have been in the office hour. So let me just back off that a little further. Yep, this is where I wanted to recap. So let's see if I can center this slightly better. Okay, can you all see it? I hope so. So we have this theorem 5, which is sort of a center point for us. And it says if we have a finite state Markov chain, the way I wrote it here, then there exists unique stationary, which looks like 1 over mi, and mi is this, the expected time it takes to go from I to I back for the first time. And in this case, we figured out what the pi is. It was pretty easy, and that gives us the mi's. And then we got to these two questions. What if the Markov chain is not irreducible? Does it still have a unique stationary distribution? And what we said there was, yes, as long as the other states, as long as you have one irreducible set of states, and the other states are all transient. So this was a simple example of that. These two states communicate with each other. So they're in one equivalence class, and 0 is transient. You can see that if you leave, you never get back. So this will also have a unique stationary. It'll be sort of concentrated on the irreducible part, if you think of that as being the 1, 2. And the probability that you're here after a long period of time will be 0. So, and we sort of made sense of that. If you think of, if you're at 0 here, the average time it takes to get back, well, to get back for the first time, you have to do it in one loop. But then there's no other chance of getting back because you can't do it for the first time in 2 steps or 3 steps or any steps. And if you regard infinity as never getting back, there's a 50-50 chance of that happening. And if you actually figured out the expected value of such a table, this would be infinite. So, and that really means M0 being infinite, 1 over M0 would be 0. So it's really saying the definition on the transient states will be 0. And then it'll just be on the irreducible states. And I think I followed this up with something like this. Yeah, more complicated example. So even though it's more complicated, it's the same idea. There's one equivalence class of recurrent states and everything else are transient classes. So that means on the transient states, the stationary distribution will be 0. On the and then on this one, it's just what we got by theorem 5. So that was one idea. And then I also at the end put this out there, that if you had two two equivalence classes of recurrent states, then there would not be a unique stationary distribution, because if you had one on this and if you have a stationary one on this, you can form a linear combination and get as many of these as you want, and these turn out to be stationary. And this is like problem 5 in the homework. So you lose uniqueness. So if you have two recurrent classes of, two equivalence classes that are each recurrent, then you no longer have a unique stationary distribution. And that was it. That's what we did last time. But there was the second question here, which I never had time to get to, and that's what's the full version of Theorem 5 about? And in there, they have the idea of a positive recurrent state. And that's what I'd like to talk about today. So any question about any of the recap? And if not, then let me just start off on this agenda to talk about positive recurrent states. We haven't talked about them in class. So, but you could have been reading well, if you read Theorem 5, it's right in there. So you could know something about it. So let me flip the page and talk about positive recurrent states. And I'm going to do it a little differently than the book does. I'm just going to give you an example up front, and then we'll go from there. So let's turn the page, add a new page. Okay, it doesn't want me to put lines on it yet, so I'll be patient and do it now. Good. Okay, so I would call the title of this lecture, I guess, would be Positive Recurrent States. So there's at least two ways to do this kind of talk. It's one, to do it in a traditional sense and just define what it means to be a positive recurrent state. And then to give examples. And I'm just reversing it slightly. I'm going to give you the example up front, and then use that to introduce the idea. So here's an example I want you to think about. And actually, you've seen it before a little bit. So let's actually say there are two examples to consider. So the first one looks like this. And keeps going. So the chance of going from 0 to 1 is P. And the chance of going from 1 to 2 is P. And from 2 to 3 is P. And that continues infinitely often. So there's an infinite number of states. So the state space here is 0, 1, 2, 3, etc. It's an infinite state space. And the probability of going back down, well, let me first tell you that this problem we've dealt with before, and it's problem 18 from chapter 1, actually. So the probability, well, from 0, you'd have to, chance of returning would be 1 minus P. And the chance from 1 of going down would be 1 minus P. And from 2 the chance of going down is also 1 minus p, and so it goes. And all these, so sometimes this kind of system, this is a Markov chain. If you look at it, it has a, how does the P matrix look? The P matrix is infinite. So I can't show you it all, but I can show you the start. From 0, you can go back to 0 with probability 1 minus p, or you can go up with probability p. And then there's 0 probability of going anywhere else. So just imagine that going up infinitely to the right. And at 1, the chance of going down to 0 is 1 minus p. And the chance of going up, well, there's no loop, but you can go up to 2, and that's p. And then 0 is the rest of the way out. Let's do one more. From 2, you can go to 0. That's 1 minus p. And the only other place you can go to 0, you can't go to 1. You can't go to 2, but you can go to 3. And then it's 0 the rest of the way out. And 3 would be similar. 1 minus p here. 0, 0, 0, and that p would occur here. And then 0 the rest of the way out. And the pattern for the matrix, I think, is pretty clear. Each row would have only 2 values, and they would look like 1 minus p going down to 0, and p going up by 1 from where you are. Okay, so I've said you've seen this before, and just to make sure you remember, it's problem 18 on page 43. So it's problem 18 on page 43, which was homework, and it may even have been on the midterm, I don't recall right now. And what did we do back then? Back then, we did parts A, B, and C of this homework problem. And part A was to say, show the chain is irreducible. That's pretty clear from the diagram. You give me any 2 states here, there would be a way to get from one to the other and back. Now, suppose the states were 1 and 3, to get to 1 to 3, just go up 2 steps and you're there. But to get to 3 to 1, the only way to get there would be to go down to 0, then up to 1. So if you're already past the state you're trying to get to, you have to go through the 0 state. But in any case, there's every state here communicates with every other state, and so it's irreducible. That's part A. Part B asks you to find the probability of going from 0 back to itself. And I don't want to go through the whole problem again, but that turns out to be 1. So, and you may even have this in your notes. The probability of starting at 0, that the time it takes to first get back to 0 is equal to, well, I'll just do this one, is less than infinity. This is what we defined the rows to be, row 0, 0. And it turns out this is equal to 1. And that's actually the topic of B and C in this problem, is to show that. And what that means is that 0 is recurrent. And since 0 communicates with everything else, all the other states are recurrent as well. So this is a recurrent chain, which means what? Actually, in this case, the chance of going from I to J is equal to 1 for all I and J and S. Okay, so this is a recurrent chain. Now, That's where this example is left off. So again, look at this, if you will, if you don't remember all the details. Such a chain has a name, and I don't remember if I gave it to you at the time, but it's a colorful name. It's called a birth disaster chain. You can see why, because you can think of going up by 1 as a birth. So that would be the P's, probabilities here. And the disaster would be falling back to 0. Another name for this, which is common, is birth catastrophes. A birth catastrophe chain. Well, disaster, catastrophe, those are both words that can be used synonymously to mean that something awful has happened. And in terms of the chain, what's happened that's awful is you've returned all the way to the starting state of 0. So wherever you were along the way, it's possible to go to just be wiped out entirely. So if this were a population, it's possible to go from any number of people in the population back to 0. Now, unlike population, most populations, if you could go to 0, you'd be extinct. In this one, you get to regenerate and start over again. But still, it's you can see the action of it. So maybe a nice example, which you could relate to, would be doing something on the computer, maybe word processing or doing something, and you spent a lot of time completing your paper, and then for some reason you didn't save it or you hit the wrong button and the whole work was lost. Most of us would consider that a sad story. And if you want to make it a little more dramatic, you can say it's a catastrophe or a disaster, because all your work is lost and you have to resume and build up. So when a computer crashes or you lose things in that manner, this sort of fits the bill. Questions about this example? By the way, Professor Swift in our department has done some work in this kind of area. So he's knowledgeable about birth catastrophe kind of bills, chains. Okay, well, I've got my usual Friday morning outdoor distraction here. So let me see if I can move along. So I guess the conclusion is this is a recurrent chain in this case. And well, that already comes through with both of these. Okay, now what I want to show you is something that looks like this, but it's a little more complicated. And that's the second example. So this is example 1. Which is just a homework problem from before. And example 2 looks like this, but is a little different. And by the way, since I think all of you have had calculus, what you probably know from calculus is things get complicated when you do things that involve infinity. Like what? Like limits, or even like integration, where you have, that's a limit as well. So when infinity comes in, life gets a little more complicated, and our intuition is not necessarily really strong. So here's where I'm going with our second example. It looks like the first, so I can start off the same way. 0, 1, 2, 3. And it keeps on going. And there are the same kind of arrows as example 1. And when I said same type of arrows, entirely the same. There would be an arrow here, there would be an arrow here, and here, and here. And this goes on forever. So it's an infinite chain, once again, just like the other one. The state space is 0, 1, 2, 3, etc. Never ending. And so in terms of how the diagram looks, it almost looks the same, but the probabilities are not the same. So let me tell you what the probabilities of this one are. This is a half, which would make this a half. This one is 2/3. So they're not the same. It's not just P. 1/2 and 2/3 are not the same like example 1. But there is a pattern: 1/2, 2/3, 3/4, 4/5 would be the next one here. And even though I've only shown 3 catastrophe arrows, there are many more, right? For if you were to, put the arrow in for 4, the states, if you put in the state space, the state 4, then there would be an arrow going back down to 0. So all of these are there. And what are they? This would be 1/3. This one would be 1/4. This one would be 1/5, and the pattern would persist. Okay, so first glance, looks like a birth catastrophe chain or a birth disaster chain. You might even want to make sure that it's a Markov chain to begin with. So let's actually do the P matrix like we did the other one. The one-step transition probability matrix will again be infinite, so I can't show you all of it, but I can show you the beginning. From 0 to 0 has probability 1/2. And then going from 0 to 1 is 1/2. And then going 0 anywhere else in one step is not possible. So it starts like that. From 1 to 0 is 1/3. And you can't go from 1 to 1. There's no loop. But you could go from 1 to 2, and that's 2/3. And then there'd be zeros the rest of the way. And hopefully the pattern is emerging. From 2, you can get all the way back to 0. That happens with probability 1/4. You can't get from 2 to 1 in one step, nor from 2 to 2. There's no loop. But you can go from 2 to 3. And that's about all you can go. You either can go down to 0 or you can go up by 1, and then the rest of the way is 0. And that's the pattern. Oh, something got messed up. Okay. So if you compare this to the one we had before, the first column was all the same, 1 minus P, and here it's not the same. It's 1/2, 1/3, 1/4. And this everything else here was 0 except for this diagonal, which is all P. And it was pretty clear that the rows added up to 1. So this was a stochastic matrix and corresponds to this diagram. Well, the same is true here. Even though they're not all the same number, the rows add up to 1, 1/3, 2/3, 1/4, 3/4, and so forth. The next one would be 1/5 and 4/5, and so on. So this is a stochastic matrix, and it does represent this. Okay, now let's explore This is the one we're really interested in today. Let's explore this a little more. If we follow the homework that we did before, let's see, let's see what they said before. Well, can't remember exactly the order, so I'll glance at it. Oh, show it's irreducible. Well, yeah, this is irreducible again. Why? Just as before, you can get from any state to any other state with positive probability. So if you're at 2 or 3 and you want to get to 5 or 10, just keep going straight up and you'll get there. And the probability will be the product of the probability along the way. And that'll give you a positive probability of getting from any state to any other. On the other hand, if you're at 3, 4, 5, and you want to get to a lower state, the only way to do it on this diagram is to fall back all the way to 0 and then work yourself back up. But the probability of that happening is also positive. So this is irreducible. So this is again irreducible. Every state communicates with every other state. All right, what was the next thing we did there? The next thing we did back for homework was to figure out row 0, 0 and to show it was equal to 1. Well, it turns out this is also true here. And let's go through that. So let's check. Check what? Let's check that row 0, 0 is again 1. And what would that mean if it's true? That would mean that 0 is a recurrent state. And what we did last time after we knew 0 was recurrent and 0 led to 1, and then we had a theorem that said that means 1's recurrent and so forth, and that gave us this. So we're trying to do the same kind of thing, even though the probabilities are not just constant going up, they're changing as you go along. Okay, so let's figure out what this would be. So row 0, 0, by definition, is if you start at 0, the time it takes to return to 0 is finite. That's our definition of getting from 0 to 0 eventually. And we can do that, as we've done in the past, by saying, well, maybe you went from 0 back to 0 in 1 step. This is the first positive time it takes to return, so perhaps you could have done it in 1 step, or perhaps you could have done it in 2 steps, or 3. Etc. Okay, so let's just figure out all this. So if you're at 0 and you want to first get back in 1 step, look at the diagram. There's only one way to do it, and that's loop. So the chance of starting at 0 and first returning after 1 step only would be the chance of looping, which would be 1/2. So this first one is just 1/2. Okay. What's the chance of first returning to 0 in 2 steps? Well, you can't loop and loop again because you've already returned there before 2 steps. So the only way to do it so that you first return after 2 steps would be going up and then going down. So that would be 1/2 probability times the probability going down. So it would look like this. 1/2 times 1/3. Maybe I'll write it like that. It's 1/2 times 1/3. So you can just write their product as this. And that would be the second term here. And keep going. what's the probability of going from 0 back to 0 for the first time in 3 steps? There's only one way that could occur, and you have to go up, up, and then crash. So that'd be 1/2 times 2/3 times 3/4. So that's 1/2 times 2/3 times 1/4, right? And this times that. Okay. And the pattern's becoming clearer. What would be the next one? The next one would be 1/2 times the 2/3 times the 3/4 times what? 1/5. And if you need to, you can go back to the diagram and see why it's that. If you're trying to get from 0 back to 0 in 4 steps for the first time, up, 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 that's 3 steps, and then the 4th step would be crashing here. And so that's 1/2 times 2/3 times 3/4 times 1/5, which is what I have. And the pattern persists. Okay, so this is the answer. This series, it's an infinite series. And we can simplify it further, so we can rewrite it this way. Rho 0, 0 is 1/2. And plus 1/2 times 1/2 times 3. Here these 2's cancel, and this is 1/3 times 4. Here the 2's cancel and the 3's cancel, and you get what? 1/4 times 5. And hopefully I've gone up far enough that you believe the pattern is persisting. The next one would be 1/what? 5 times 6. 1/6 times 7. And so it goes. Okay. Now, now it turns out we've done this in class before. We can write this one as 1/1 times 2 if you like. That doesn't change much. And where have we done this before? It's always good to point out something we've done before, especially if we did it. So let me see if I can find that. Okay, first sweep, I don't see it, but I know it's somewhere in chapter 1. So I'm just going to do a little search. I think it was later than sooner. Okay, so it actually occurred on page 33 in example 13. So people are taking notes. I'm going to do it again anyway. See, what I just say, page 33. Example 13 from the book. And we did that example in class. So if you take notes, I hope you do, that would be somewhere. Okay. So let's, but I want to do it again. First of all, it's not hard to do again. It's a nice example to do again. And so let's do it again. Now, what we really have here is something that looks like this. This looks like the sum of a fraction that looks like 1/n times n plus 1. 1 times 2, 2 times 3, 3 times 4. So it looks like the product of 2 consecutive integers, positive integers. And the sum starts at 1, and it goes on forever, an infinite sum. So what we're doing is that kind of sum here. The approach that we did before and that you may want to remember is we used partial fraction decomposition. And that's something from calculus, usually the second quarter or semester. And how it goes is this way. If you have something that looks like this, which is called this is a rational expression, and if it's already got the denominator factored, which it does, this could be written as some constant all over the first factor plus some other constant all over the second factor. By the way, many of you are math majors, well, most of you, I assume, and you might ask, why does this work? Or is there a reason why this works? And there is, but usually in calculus, we're going through calculus so quickly that they're just happy for you to understand how to do it rather than why you could do this all the time. I'm not going to talk about the why, but I am pointing out that it's a tool that happens frequently enough that you might want to look into it sometime just to see, why this works. In this case, this is how it works, and A and B are constants. Okay, so then the game is to determine the constants. And why you use this in calculus is if you're integrating something like this, it's easier to integrate each of these. So this becomes a tool for integration in calculus, but it's an algebraic result that lives on its own and with or without calculus. So, but how do you find A and B? Different ways, the way that we did it last time. I cleared this of the fraction, so I multiply both sides by n plus 1. If you multiply both sides by n times n plus 1, the left side just becomes 1. The right side, the n cancels, and you get a times n plus 1. And over here, the n plus 1 cancels, and you'll get b times n. Okay, so assuming this is, the true situation here to begin with, then you can get here. And then what I usually do, the method I use, is let n be different things. So if n is minus 1, because this has to hold for all n. If n is minus 1, this term goes away. And what you get is b times minus 1 is equal to 1. And that implies that b is negative 1. Okay, so that nails one of the constants. And then the other nice way to do this is if you let n be 0. In this expression, 0 times n goes away. And this becomes 0 plus 1, so you just immediately get a plus 1. So in this case, it's not hard to find a and b, and you can write it 1 over n, and then this is minus something like that. And if you have any doubts, you can subtract the two fractions by getting a common denominator, which would be the product. And when you do that, you do end up with this. So it's easy enough to see that this is true. But what does it mean? It means the sum that we're after. And by the way, in our case, the sum has meaning. The sum is equal to rho 0, 0. So we can say rho 0, 0, which equals the sum from 1 to infinity. We can simply put in what the partial fraction decomposition tells us here. This is the same as 1 over n minus 1 over n plus 1. And if this looks familiar, good, because we did do it once. If it doesn't look familiar, good also, because now you got a second chance to understand it. This is an equal sign. And the neat thing about this is it's a telescoping sequence. Telescoping series. Telescoping series are one of the few kind that you can actually sum without thinking too hard. The other kind is geometric. There's formula for that. So let's see why this is easy to sum. When n is 1, this becomes 1 minus a half. So the first term of this series is 1 minus a half. The second term would be 1/2 minus a third. The third term would be a third minus a fourth. And it continues in that manner. Infinitely far out there. And this cancels this, and this cancels this, and this will cancel this. And so in general, what this will turn out, the only thing that doesn't get canceled is the lead term 1. And what's out there, if you stopped at n, if you stop the sum at some capital N, what you would have would be something like 1 over n. But you're not stopping you're not stopping the series at n. So what you're really doing is taking the limit of this as n gets large. And 1 over n gets close to 0, so this gets close to 1. So this infinite series that looks like this equals 1. And so we get the interesting answer that this is 1. Okay. Now, it's more than a consequence that this is adding up to 1. This was sort of cooked up in order to make this work. And so it's a nice example of a birth disaster kind of chain where the P isn't constant, the P is varying, and yet you still have the same result that we had in example 1, because in example 1, we had that rho 0, 0 was also 1, that the chain was recurrent. We can now go back to this and make the same conclusion. This chain is also recurrent. This Markov chain is a recurrent chain. And how does that argument go? Same way as it did for the homework problem. Once you know 0 is recurrent, and we just went through that, 0 leads to 1. So we have a theorem back in chapter 1 that says if 0 is recurrent and it leads to somewhere else, then where it leads to is also recurrent. And the chance of getting from this to this eventually is 1. So that gives us 1 is recurrent, but then we can use that again and again. 1 leads to 2, 1 is recurrent, that means 2 is recurrent, and the probability of getting from 1 to 2 eventually is 1. So in the same sort of way, we can show that all states are recurrent here. Recurrent. Any questions so far? This again would be called a birth disaster, birth catastrophe chain. But it's not like the one we did for homework, because the one we did for homework was just simpler. It had just the birth rate was constant p. Here the birth rate is changing. Okay. What I want to discuss now is what's involved. So we sort of want to get to the question is, do these have stationary distributions? We could ask it in both cases. Does this thing have a stationary distribution? Because that's what we're studying in the chapter we're in, chapter 2. And then we could also ask the question, does this have a stationary distribution? Now, since theorem 5 says in order to have a unique stationary distribution, you sort of need to have an irreducible chain, and both of these are irreducible. So what does theorem 5 give us in that case? Theorem 5 if I just can paraphrase it, would say that pi at any point I would be 1 over mi, where mi is what? Where mi is the expected time if you start at I, that takes you to first get back to I. Okay. So why don't we do this for both examples 1 and 2? Why don't we just do it at 0? So let's figure out, let's find pi 0. Well, not quite. Yeah, pi 0, that's right. But pi 0, according to theorem 5, if it exists, would be 1 over m0. Okay, so let's find m0 for each case. I don't think we've done it for either cases, so let's do both. Let's first do the first example. So for the first example, if you wanted to know, well, there's a table to make. Here's the variable, the time it takes to get to 0. And we're assuming that you're starting at 0. And it's the first positive time, so you start at 1 here. And now if we go back to example 1, what's the chance of getting to 0, back to 0 for the first time in 1 step? Well, that would be this loop, which is 1 minus p. And what's the chance of doing it in 2 steps? Well, scroll up again. We're in example 1 at the moment. So we're going to first get back from 0, go from 0 to 0 in 2 steps. We would have to go up here and then come back. We can't loop twice because we get there too soon. But you can go up and then down, so it's p times 1 minus p. P times 1 minus p. What about in 3 steps? In 3 steps, we're back in example 1. You want to start at 0 and first return after 3 steps. You'd have to go up twice and then come back. There's no other way to first do it in 3 steps. You can't loop 3 times because you get back here too soon. You want to go from 0 back to 0 for the first time in 3 steps. That means you have to go up twice and then crash. So that's going to be p squared times 1 minus p. P squared 1 minus p. And the pattern is pretty clear now. If you want to, we're doing it in 4 steps, you'd have to go up 3 and then crash. And so it goes. So in general, if you wanted to go from 0 back to 0 in n steps, you'd have to do p to the n minus 1 times 1 minus p, right? Okay. And the table goes on forever. The probabilities go on in the same manner that you've seen them so far. And if you want to find the expected value, which is what we're after, what do? We multiply this column by this column and add. So I'll make that third column, which is t0 times the probability of starting at 0 that t0 is n. And n could be 1, 2, 3. So this product here, this times this is 1 minus p. This times this is 2 times p. Yeah, I don't think I need all the parentheses. Maybe I do, but 2 times p times 1 minus p. And this would be 3 times p squared times 1 minus p. And 4 times p squared times 1 minus p. Maybe the third should be. And in general, when you get down to here, it'll be n times p to the n minus 1 times 1 minus p. No, don't do that to me. Okay. Let me see if I can recover it. Sometimes I think OneNote has a mind of its own. Let's see if I can recover this. Yeah, I can. Okay, so did I lose much? No. But do I want what I lost? Sure. So let's see if I can recover that. Yeah. So the last one down here, let's see if it lets me do it or not, was, you keep going down. And this product was n times p to the n minus 1 times 1 minus p. Okay. And it keeps going. Now, so what is that the expected time to return? So the expected time, and we're doing this from 0 to go, expected time, expected value of t0 would be this sum. So it's, well, they all have a factor of 1 minus p in it, so I'll just put that outside. 1 minus p times 2 times p plus 3 times p squared plus 4 times p to the third, etc. And in general, you'd be doing plus what? N times p to the n minus 1. And the sum never stops. Okay. Now, we also did this before, but time is getting shorter, so I don't want to repeat all of that. So I'll just say, I'll leave that one to you. So homework. Determine this thing. Determine that factor. Hint. Well, the hint is twofold. One, we've done it before. And the idea was to differentiate a geometric series. When you have a geometric series involving just powers of p, if you differentiate it, those powers will swing down, and that'll give you a formula for this. But for now, I'll leave that as something, since we have done it before, and I'll leave that for either office hour or some other time, because I really want to. But I guess, let me see, do I really know what the answer is? Not offhand, I'd have to think about it a little bit. Another way to do this, by the way, is to realize that this is a geometric probability table. So from stat 2200 or someplace, you probably already figured out the expected value. But let me leave it that way. So at this point, I'm content with this. But I will tell you that this number turns out to be finite. So the answer is finite. Okay. So now what I want to do with the few minutes I have left is to redo this calculation for the second example. So I was doing this calculation all presuming this, right? Now, the one thing about this example, P is never specified. In a way, what's easier about this example is all the probabilities are specified. So let's redo the same idea for example 2. So this is almost done, and it will be done once you finish the homework. Let me see if I can press my luck with this page and try to stay on it. So let's repeat the calculation. But this time, for example 2. Okay, no, it doesn't like it. Yeah, so I think I got the message. It doesn't want me to do all of this on the same page. So I will move the page over. First of all, I've got to share it with you so that you can see where I am. Okay, I'm not going to repeat what I just said, but I'll say what I'm not going to rewrite it, but I'll repeat it. We're going to do it again for the second example. So let's just go to the next page, add a page here, put some lines on if we can. Good. Okay, so now we have a clean slate to try to work with. And I guess we should write down the example. So the example looks like 0 and 1 and 2 and 3 and so forth. And this was 1/2. And this was what, 2/3. And this was what, 3/4. And so that continued going up. Next one would be 4/5. And this was 1/3. This one was what? 3/4, 1/4 rather. And this one was what? 1/5. And that's how these catastrophe probabilities looked, and it keeps going forever. Okay. So that was this example. We're still trying to find M0, which is the expected time it takes to go from 0 back to itself for the first time. But this time it's all numbers, so it might be easier in a sense. Put in T0, we start with 1 and 2 and 3, and go from there. And this is the probability that T0 is anything on the list. You can write it as X or N, maybe N would be better. Well, I'm going to use N for something else, call it K then. Okay, so and there's a loop here that I neglected to put in. What's the probability of going from 0 back to 0 in one step for the first time. Well, that's just the loop. So this is 1/2. What's the probability of going from 0 back to itself for the first time in 2 steps? Well, you got to go up and then go down. So that's going to be this 1/2 times 1/3. Okay. What's the probability of going from 0 to 0 for the first time in 3 steps? Well, you'd have to go up twice. Let's see. Yes, and then you'd have to go down. So when you do that, it'll be 1/2 times 2/3 times 3/4. So that'll just be this again. What survives? 1/2 times 2/3. You just get 1/3 times 1/4. This times this, 1/3 survives, and that's that. And the pattern is that way. So 4, if you wanted to go up 4, do it in 4 steps, 1, 2, 3, 4, you'd be multiplying these together, but the 2's here cancel, the 3's here cancel, so you have 4/5. And that's the pattern. So that's what makes this example sort of nice. So in general, if you went out to the kth term, it would be what? 1/k times k plus 1. Okay, so now with this table, if we wanted to find the average, we'd multiply the variable times the probability that the variable takes that value. So it'd be 0 times 1/2, which is 1/2. It'd be 2 times this, the 2's would cancel, that would be 1/3. It would be 3 times this, which would be 1/4. This times this would be 1/5. And you see the pattern. Dot, dot, dot. Here the k is canceled, and this is k plus 1. Doesn't look what it is. And this goes on forever. And the expected value would be the sum of the series. But do you recognize the series? The series looks like 1/2, 1/3, 1/4. And so it goes. Well, that's everything in the harmonic series except for the first term. So that's going to be what? Infinite. So what do we have here? In this example, M0 is the expected time it takes to go from 0 back to itself for the first time. And that's turning out to be infinite. Okay. And this is interesting and weird at the same time. Why is it interesting? We already know that 0 is recurrent. So we know the probability of going from 0 to 0 is 1. Why? We already calculated that for both example 1 and 2. But we're just talking about example 2 here. So we know 0 is recurrent. Which means what? Which means the probability that you return will be certain, probability 1. But if you have to somehow reconcile that with this fact. You know you're coming back, but the average time it takes to get back is infinite. That seems to be contradictory, right? I mean, for certain you're coming back, but the average time it takes to come back is infinite. It seems like one contradicts the other, but it turns out they don't. So this example is interesting because basically of these two facts. It's possible to have a recurrent state, which means for sure you're going to get back, but it may on average take infinitely long to get back. Since this is odd, the situation when this occurs, when these two things occur like this, 0 is called null recurrent. So it's like it's recurrent, but it's not quite living up to our expectation of what, well, that's a pun, but not living up to the what we think the expected value should be. We think the expected value of something that's got to come back should be finite. So this thing, you've got to come back, but the average time it takes to do it is infinite. So this is called null recurrent. Whenever you give something a name like null or negative or anything that sounds negative, that means you don't like it that much, or you consider it as an oddity. And that's what people considered this to be when they first discovered it. I don't view it that way. I view it as interesting that you could have a recurrent state and still take infinite time to come back is interesting. But what does it mean about having a stationary distribution? The stationary distribution at 0 is going to be 1 over m0. But m0 is infinite. So what it means in this example, that if there's a stationary distribution, it is signed 1 over infinity is thought of as 0. It would assign 0, the probability of being at 0 to be 0. Now, it turns out that the same kind of theorem holds for as before. All these other states are also recurrent, but they're also null recurrent. So like it's inherited, which makes some sense, because if it's taking you infinitely long on average to get back to 0, it's going to take you infinitely long to get back to 1 as well. They're only 1 apart. So all these states are null recurrent, which means they all have stationary distributions that look like 1 over infinity, which means they all look like stationary distributions that are 0. But that can't be. Why? A stationary distribution has to add up to 1. And so what it really means is this guy doesn't have a stationary distribution. Because if it did, by theorem 5, they would all look like 1 over mi, and it turns out all the mi's are infinite, and you add up a bunch of zeros, you can't get 1. So there is no stationary. So that's the takeaway. Came about 5 or 10 minutes late, but it's there. The takeaway is what? There does not exist a stationary distribution. For this example. By the way, that's not the conclusion when you go back and do your homework problem. The other one does have a stationary distribution. So this example 1 and 2 are really in contrast to each other. One has a stationary distribution, the other one doesn't. So if you don't like something, you call it null recurrent. On the other hand, if this doesn't happen, if you make sure that the time it takes to get back is finite, so if m sub I is finite, less than this, then state I is called positive recurrent. Okay, so now we finally get the word that occurs in theorem 5. So in theorem 5 says, as long as the states are positive recurrent, which means what? It means that this mi is finite. The average time it takes to get back is finite for all I. Then it'll have a stationary distribution. Okay, well, there's more to say, but I basically overused my time anyway, so let me stop here. I'm happy in this sense. This is a counterintuitive kind of concept. And so now I've given you an explicit example of when it occurs. One last word. if you're in a finite state space, you can't have no recurrent states. So this phenomena that I just described only occurs, it doesn't occur all the time, but occurs occasionally in the infinite state space case. All right, so let me end it there. Any quick questions before we just take our break and go to office hours? The takeaway, I hope, would be this example is interesting. And it's not quite like the homework problem 18 that we did before, where all the p's were constant. By having the p's vary in this manner, we're ending up with a chain that has what? Recurrent states, but they're null recurrent states, meaning that the time it takes to get back are infinitely long. And that means it has no stationary distribution. And if it has no stationary distribution, then it has no steady state. Okay, let me say goodbye to those who need to move along. And for those who are interested in staying for the office hour and whatever we talk about thereafter, should probably be more on this stuff. I'll see you in about 20 seconds after I get some water. I think I'm out of water. Okay, that's no good. So, wow. My wow comes from feeling the plug on my computer. It's hot. So, well, thankfully my computer is cold, but the plug is really warm. Okay, so any questions on today's lecture, which is still, part of it's still available? Any questions on any of it?
Yeah, I have a quick question about what we just went over.
Sure.
I guess it is a little not very intuitive, but if m not, if the expected time to go back to state 0 is infinite, that still means there is a chance that, or that will go back to that state.
Oh yeah, not only is there a chance, the chance that you're going to go back is certain. Okay.
Right. Well,
Yeah.
I guess the expected time it takes to get back there is infinite.
Correct. I'm smiling because you're right on, spot on. Okay. It seems like these things are contradictory, right?
Right.
If you know you're coming back, for sure, with probability 1, you're going to start, if you start at 0, you're going to come back to 0. That has probability 1 of happening. It seems contradictory to be told that the average time that it takes to get back is infinitely long. Okay. And I guess, well, if it helps, I don't know if it helps at all, but suppose you simulated this. And so you could simulate this kind of thing, and you can say, you can run it over and over again, assuming you start at 0. And suppose you do, and the first time it takes to get back maybe 8 steps. I'm just making these numbers up. And the next time it takes you, I don't know, 15 steps to get back from 0 to 0. And maybe there's some small numbers in there too, like 3. Maybe you can do it like that. So if you simulate it over and over again, what does that mean? Pretend you're at 0, pretend these are the probabilities of advancing and retreating, and then just see how many steps it takes to first get back. What we're saying is, these are realizations of how long it takes to first get back, but if you were to average these numbers, the number you get by averaging them is getting, if you did it more often, is getting bigger and bigger. The average time it takes to get back is infinite. So there's some, and in a way, why does that even happen? It happens because is in the case that you get to move along, say you get to move along to 3, then this chain is pushing you upward, right? The probability is getting bigger as you go further along. And so they're sort of forcing you to take longer walks or longer. Now, it's almost, yeah, it's forcing you to go up with the reality, the chance of catastrophe is there always, but getting smaller and smaller as you get further along. So that sort of explains it a little bit, because this is pushing you upward, and yet you always have a chance of collapsing. The probability of collapsing as you get further along is getting smaller and smaller, but you know, if something even has a 1 in 100 chance, it happens 1 in 100, in that case, you're all the way back here. So that's explaining why it's recurrent, because this thing of happening does happen. And it also explains why it sort of promotes long journeys away from 0, because once you get a little bit away from 0, there's a push upward, which encourages you, you know, there's more of a chance of going up than down, much more. 80% here versus 20, and it even gets, you know, higher and higher. And what that does is contribute to the general average. By the average time, it's becoming as big as you like. But if it seems contradictory and counterintuitive, it is. And to be honest, that's what I like about it. Okay, because when infinity comes into the picture and it challenges you to try to reconcile things, I mean, it's in a sense the same idea that you have to worry about in calculus. In calculus, you see the harmonic series equals infinity, and you see this, right? And this thing equals what? Pi squared over 6, or converges is the main point. And that's a similar kind of, whoa, my intuition needs some readjustment here. This doesn't look that different than this, right? The form is very similar. The only difference is there are squares here. There are no squares here. And this thing adds up to an infinitely large number, and this thing converges to a finite number. And you're left thinking, they don't look that different, but the results are really different on the right side, okay? And so I think this is, so I think going on with math, and especially dealing with infinity, is a continual recalibrating our intuition with regard to infinity, because it doesn't look at first glance that these should go like this way, but they do. And I mean, you can do the same analysis. You can say, well, these numbers, you've left off many of these other, but it's still hard to, you're ended up having to go back to the proofs. You know, why does this equal this and why does this equal that, to try to really grasp what's going on here. And this is similar. How is it possible that a state could be recurrent? So you know that with what probability 1, you'll be coming back. And yet the average time it takes to first come back is infinity. So my way of trying to explain this is to provide you this example, because the book's way is to first define it, and then they don't really give you an example of where it happens until you get to birth-death chains. And birth-death chains are more complicated than birth-disaster chains. So I'm trying to provide you an example of where this occurs. And that's what this lecture was about. And now, yeah, now you have to deal with it. Okay. But
Your explanation did help. I think I'll just have to still think about it a little more.
yeah, no, that's totally totally reasonable. That's the kind of reaction I'm hoping for, is that you just say, this has something that seems contradictory. And yet what I've done in this example is correct. So we have to adjust our intuition a little bit in some manner to realize that such things could occur. Other questions? And it's interesting, the last thing I said, it's interesting that if you live in the world of a finite Markov chain, then this doesn't occur. So these no recurrent states, such as given in this example, and by the way, in this example, 0 is no recurrent, so is 1, so is 2, so is 3. All the states are no recurrent in this example. And that will be the case if you have an irreducible, infinite collection of states. If one of those states is no recurrent, then all the other ones will be as well. So no recurrent is a little bit like being between transient and recurrent. Okay, transient means there's a positive probability you never get back. And recurrent means the probability is 1 that you'll return. And no recurrent is sort of in between, because it's saying the probability is 1 that you'll return, but you may have to wait a real long time to get it to actually occur. On average, it's infinite. But still, it will have probability 1 of happening. So it's sort of in between. So now we have 3 classifications of states. They could be transient, which means we intuitively there's a positive chance of not returning. There's recurrent, which is saying the chance of returning is 1. And now there's no recurrent, which is saying it's like recurrent. There's a probability of 1 of recurrent, but it's like being transient in that it's taking infinitely to return is hard to even think about, right? If someone says it takes infinitely long to return, you almost don't even think of that as returning, right? So that's how it's sort of a midway state. Okay. Should I? Well, let me see. So if I haven't already made it clear, this is the simplest example I know of a no recurrent state. If you were to say, oh, can you show me another example, a simpler one? I don't have a simpler one. And why is it got to be this, or it's got to be this or something more complicated? Well, because of what I've already said, there's a theorem that says no recurrent states only happen if there's an infinite state space. So you have to have an infinite number of states to have a no recurrent state at all. And if you're going to have an infinite number of states, this is about as simple as it can get. And you want it to be irreducible. So you want each state to lead to each other. And so if you think about it with those requirements, I have about as few arrows as you can possibly have, right? Just enough arrows to make sure that it's irreducible, and enough states to make it infinite. Okay, so what I'm suggesting is, well, I don't know an easier example. If anyone learns of an easier example, I'd love to see it. And this example, to get the results, well, okay, to get the results that the average time is infinite just comes back to calculus, because it comes back to the harmonic series being infinite. So that's not too bad, because, well, I don't know. Is the harmonic series being infinite part of your view of calculus? If it is, then it's not too bad. If the harmonic series being infinite is also counterintuitive to you, then this result is built upon another result that doesn't seem that likely. But okay, it is built upon the harmonic series diverging. And the other part of it, the other part which we did, let me see, where did we do that? Previous slide. Was this part here, that it's recurrent is sort of nice because it comes out of this telescoping series argument. I'm trying to see if there's anything here you might want me to talk about more. I also have the homework problem I gave you, which is here, is actually something we've already done. It's to sum a series that looks like the derivative of the geometric series. So we can do that again if you would like. And there's no problem with that. The reason I didn't do it is because I wanted to get to the example on the next page, because that's the new stuff, really.
If nobody has any questions about what we went over today, I have a question about the algorithm we went over for calculating stationary distributions.
Sure. Well, yeah, let's, okay, so that's a different direction. So let me just give anyone else an opportunity first. Is there anything that we've done today or a little homework problem from the book that people would like to go over? And if not, then I'm happy to talk about the algorithm. I'm happy to talk about it, even though I don't remember it off the top of my head, but anyway. Okay, sure, let's go for the algorithm. Let me get a clean page. I think that would be a good idea. Where am I? Yeah, that's the one I did today. And there's probably nothing past that, I don't think. So let's just add a new page. Sure. Do you want to help me out and just tell me the algorithm?
Let's see.
I can look at that, but it's a little complicated.
I think it was where we had our one-step probability matrix or one-step transition matrix, and then we replaced the last column.
Yeah.
P tilde with the three ones.
Yeah, I remember that. All I'm really asking for is the last line of the algorithm. But it's like, I can do it. All right, if I were to guess, I think there may be a minus identity in here.
Oh, I think it's, yeah, P tilde minus I to the inverse transpose.
That's the part I wanted to make sure. Then it's times some other thing.
Some vector V.
And what was V?
It
was P tilde of something, right? Maybe P tilde of 0, 0.
P tilde transpose and then 0, 0, 1.
Yeah.
Oh yeah, all those zeros and then last one's 1.
And then what is all this equal to? U's? Or a vector, I don't know what I called it, but I think it was a vector that looked like this. Is that more or less correct?
I think that's what I have as well.
Wonderful. Okay, so now that's the part. Actually, I'm trying to think how to remember this. For me, yeah. I might just bite the bullet and just memorize it, but okay, go ahead.
I wanted to ask why P tilde minus I is invertible.
Oh yeah, that's a key question. And what that reduces to, so it comes back. So I can give you only a partially only a partial answer, okay?
Mhm.
So the original, let's just think of it in terms of a three-state example, because already that's enough, then the answer is there. So 1, 0, 1, 1. Oh, I'm sorry. Let me write this the right way. I got the notation wrong. So suppose it was P 0, 0, P 0, 1, P 0, 2, P 1, 0, P 1, 1, P 1, 2, P 0, 2, 1, 2, 2. Okay, so if we're in the 3 by 3 case, what we're trying to solve is this system of equations. And vector pi in this scheme we think of as being pi 0, pi 1, and pi 2. And we're insisting that this be a distribution. Okay, so what it turns out to be is a matrix P like this turns out to have rank n minus 1. So there are n states, assuming there are n states. And usually they just call them 0, 1 up to n minus 1. It turns out that this thing has rank n minus 1. And that's the part I have to think about. If you're going to ask me why that's true, that's sort of the key to it, which really means, what does it mean? In terms of linear algebra, if you were to try to do, turn it into row echelon form by using, adding and subtracting the rows and columns in a variety of ways, you wouldn't be able to get it to be completely a triangular matrix. Or said another way, there are two of these rows here that are really the same equation in disguise. But that's a good question. Why is that true? But for the moment, just assume that's true. That means that if we try to solve the system of equations given by this, we won't have enough information because there's only n minus 1 of the equations that are different. And so what I'm doing in this to get this algorithm, I'm assuming that if I kick out one of these equations given by this and replace it by this equation, that then I have n distinct or independent, actually is the word, equations, and then you could take an inverse. So, and that's being reflected already when I go to P tilde. P tilde changes the last row, column rather, to be all ones, and it changes this equation so that when you multiply by pi by that final column, you're getting a 1 in the position over here. So I'm changing the fundamental equation to be different, and be different in an important way because I'm making sure I have n independent equations. And once you accept that that's the story, then the rest just flows, okay? Because what it really means is that this thing is invertible, whereas this I'm sorry, yeah, I got P tilde twice. So put it in words, P is not invertible because it doesn't have full rank, but P tilde will be. And that's what's being used in this algorithm. So I think it boils down to, how does one know that this has rank n-1? And I'll have to think about a good answer for that, if that's what you're asking. I think that is what you're asking. And well, I guess it's a two-parter. Why does this have rank n-1? And why does kicking out one of these equations, and by the way, you can kick out any one you want. I just chose the last
Okay.
one, the last one for convenience.
That was gonna be one of my questions as well. Like, why was always the last one?
Doesn't have to be. I
Okay.
just did it for convenience. It could be the first one if you prefer, somewhere in between. It should all work the same way, because you're really just saying, yeah, you're really introducing a new equation that's independent of the others, and the others are a dependent collection. So yeah, I'd say, let me think about why this is rank n-1. I've been there before, but I don't remember right off the top of my head why that's the case. You might, I mean, you certainly see it if you take it. Okay, so here's a practical question. The theoretic question is out there. Now I have to think more on that. But if you did a 3x3 example and you tried to solve this system without this, you'll get things like pi0 equals pi0, which are true, but useless.
Right.
So you won't have enough information to nail down what the variables are. And so from an experiential, from experience, what I'm saying certainly is easy to check. Just try to solve a 2x2 or a 3x3 without using this equation, and you'll see that you just don't have the equations that you have are not enough to nail it down. But why it's rank n-1? It could be rank n-2 or something like that, right? That I'll have to think more about. But it's a good question. If it is rank n-1, then the rest sort of makes sense. If you're introducing a new equation that would up it up, and then the invertibility comes in here. But once you know this is invertible and this is invertible, then it's not hard using linear algebra to get this thing to be invertible.
Right. So if we had a Markov chain that's irreducible in finite state, then it should be the case that the one-step transition matrix P will have less than full rank.
That's correct.
Okay.
And by the way, I don't think it has to be irreducible. I think any Markov chain, the P matrix will have rank n, if they're in states, will have rank n-1. So irreducible or not, but in the theorem's case, the theorem's telling us that the irreducible case, there will be a unique answer.
Okay.
And if it's not irreducible, then there won't be a stationary distribution, but that's for other reasons. Okay. And that's a little bit like example 5 in the homework, which we touched on. Yeah, so I'll have to think about why it's rank n-1.
Sounds good. Thank you for the answer, Professor.
You're welcome. I'm sorry it's not complete, but that's I think I knew more in the past. I'll have to rethink it. This whole thing with this algorithm, I had to rethink it this whole time through, because I didn't have it written down, and I knew there was one, and I don't know where it is in the literature. I'm sure it's there somewhere. Well, I'm not sure, but pretty sure. So that would be another way to go. So here's another way to go. Google it. Why, why is the one-step transition probability matrix of a Markov chain an n by n probability, one-step probability matrix? Why does it have rank n minus 1?
Is there a name to this algorithm as well?
Not that I know of.
Okay.
I'm in a weird position on the algorithm because I've taught it before, I've realized it before, out of necessity, because I didn't want students, if you don't have something like this algorithm, and if you're doing stuff by hand, then from a practical point of view, you're almost limited to the 3x3 or the 2x2 case. Because if any higher dimension, solving systems of equation, or either that or what, assuming more linear algebra than I've assumed. You could, if we assume more linear algebra, then you could do it by converting the matrix into row echelon form. But I didn't assume that. So I was looking for initially a way that students could use their calculator to get the stationary distribution without having to solve a system of equations. So I don't know if it has a name. I actually haven't seen it before, because somewhere along the line, I realized that we had rank n minus 1 and I could make this work.
Okay.
And that's so I think looking for the algorithm would probably be a harder way to go. But though it'd be interesting to me if you actually found it somewhere. So let me know if you actually do. But asking why a transition probability matrix has rank 1 less than its dimension, I think that's sort of the key to what you're asking, and that should be something one can Google and hopefully get a good answer to. I may do it myself, but if I don't, I recommend that you do, and if you find anything, let me know.
All right.
Thank you.
Thank you again, Professor.
You're welcome. Other questions?
Will we ever worry about invertibility, matrix being invertible or not during like a test, or will they all be invertible?
Oh, this algorithm is what I need you to know. So I don't think the question of invertibility will come up on the test. I mean, I may have to walk that back if there turns out to be a real easy answer why this is. Yeah, if I learn more and we all learn more, then maybe that'll change, but that's not what I intend at this point. At this point, I'd like you to use this algorithm to find the stationary distribution. And so what I'm more concerned that you know how to do is know the algorithm and know how to use it on a calculator. And that presumes, invertibility is presumed. Once you write this thing down, you're taking the inverse of something. Okay, so it's on. I don't think the discussion I just had is likely to be test material kind of stuff. But using the algorithm would be.
Yeah. Okay. Thank you.
Yeah. I mean, the only other thing I did today, which offers any new homework, is that business about summing the geometric series after you've differentiated. Is there anyone who wants me to go over some of that? In other words, the only homework problem I assigned. If you want me to do that, that would be fine. Or if you want to try it yourself, that's fine too. Either way. Okay, since interest is not strong, at least that's how I'm interpreting the silence. I think we're done unless anyone has any other questions. Cool.
No.
Okay, so
I'll see you on Monday, and I'm gonna over the weekend try and figure this
Okay.
out.
yeah,
I'll give it a shot.
it sounds good to me. Have a good weekend to all of you.
Okay. Bye, Professor.
Bye.